Get on home, yeah. Get on home, Get on home, yeah. Oh, yeah. Get on home,
From DataStax, this is the Distributed Data Show podcast. And hello, everybody. Welcome to this week's show of Graph Data and Code with Denise and David. I am David Jones-Lardy. And with me, as always, is... I didn't pick a word. What did I do? I've got to... Let's hold on.
Look at that. All the setup.
I can't believe I did this.
It's all good. It's all good.
It would also help if I spell the word thesaurus correctly. Here, we're going to go back to this one. Let's see. The unbelievable Denise Gosnell.
Oh, thanks, David.
All of that to just have me do that one thing. Anyway, yes, so I'm joined here with the unbelievable Dr. Denise Gosnell.
I appreciate that. Thank you. Yeah, today's kind of an exciting day, David.
Today is exciting because we spent all last week, right, building stuff up for what we're going to do today.
Yes. Yeah. Last week's episode, we didn't do much code, but we did a lot of really diving in and trying to think about why paths are really awesome to solve with graph databases. So if you missed that, we did a ton of setup that provide a lot of context for today. The TLDR is that we have a new data set. It is people who rated how much they trusted other wallets on the Bitcoin OTC network. And we are going to find shortest paths from one user to 1337, a little bit of a leap joke in there. Finding shortest paths between users to 1337 to figure out how much they trust each other. So that's the short version of what we did last week. And we really dove into the art of pathfinding and how to do it and why it's awesome. And we're going to see the code for that today. And the other exciting part, David, is that after we get through shortest paths today, we have kind of gotten through the fundamentals of the main templates of what people are doing in production with graph databases. So can you believe it?
Wow. Now that you pointed it out, no, I had to take a moment to grok about that. So that means we're wrapping up pretty soon, aren't we?
We are. So we've been going through three common templates, right? So we started off a long time ago with neighborhoods, and then we spent some time doing trees with roots and leaf queries. And today we're wrapping up how to do shortest paths. And those three patterns, neighborhoods, trees, and paths, are the fundamentals of what most applications I've had the honor of working on are doing in prod. So with that, you can apply those together to get into the final set of what we do in our book, And that final set is how Netflix does recommendations. But when we get there next week, we're just going to set it up for you and show you where to go to get it started. But that's going to kind of be where we end our journey on this podcast. So.
All right. So today we're gonna continue in our journey in chapter 8. We're actually gonna do this stuff now as compared to just looking at Lucy charts. And then next week we're gonna finish up the show and tail it off with the stuff from chapters 10 and 12. Right?
Yes. Yep. Just kind of setting it up so that you guys know where to go to get your hands on all that code and content, where if you're curious how Netflix makes those recommendations work, we take you all the way through it. But it applies the 3 patterns we've been working through this whole time. So if you want to take the lessons that you've learned, apply them to a new problem, we're going to leave that to you for going through chapters 10, 11, and 12. So It'll be awesome. And as usual, if you all are just now joining for the first time, or you might not be on one of the platforms, we have a few screens pulled up over here. So pardon my switching all the time. Over here on this monitor, I am monitoring questions coming in on our YouTube channel. So DataStax's YouTube channel. I think, David, you also have DataStax devs pulled up too, right?
I do. Yeah, we're definitely monitoring stuff on DataStax devs, the YouTube channel, and LinkedIn. Yes,
LinkedIn tends to get chatty. So I absolutely love it. If you guys are wanting to join the conversation, I'd follow on LinkedIn. We tend to get, I think last week we had almost 40 comments on there. Going back and forth, talking about different things during the show. So if you want to join the conversation, I think that's the place to be. But otherwise, we're going to be diving right in today.
All righty. All right. With that, I have shared my screen. And by the way, if you are joining us for the first time and you're wondering, where is this stuff that you're showing? And, where are we getting this from? I'll drop these links down here. But if you go to github.com/DataStax/graph-book, you'll see that link up there in my bar, and I will drop this as well. Graph book repo. I can only type.
Only can do one thing at a time. Yep.
Right.
But yeah, we're going to start pasting some of these links into the comment section of these different channels. So I think you just put that on the DataStax Devs channel. I just saw it pop up on LinkedIn, so you guys know where the code is. And for those of you who maybe don't want to go through a local install of Cassandra and DataStax Enterprise Graph, I get it. You also can go to DataStax Desktop. And David, if you grab the link for downloading DataStax Desktop, I will tell them about it while you do this post as well, if you don't mind.
Yeah.
So where you're watching David go is David's going to grab a link for downloading DataStax Desktop. And DataStax Desktop is a way to have different stacks that spin up and load everything you need to go through these examples. So if you have Docker on your machine, that's all you need in order to have like a one-click, go make some coffee and come back and the examples will be ready kind of experience. So hop on into downloads.datastax.com, grab DataStax Desktop. And what you can do is you can download that as long as you have Docker. You can grab the graph book stack, fire that up, and it'll load all the data, load the schema, and basically get you to the notebook view that David is at so that you are ready to go and just ready to run some queries and not have to worry about any kind of configuration or data loading or any of that stuff. So looks like thanks for sharing all of those, David. So I see them come up on LinkedIn and YouTube. So if you guys are out there looking for links, that's where they just went. So yeah, let's get to some queries, huh?
All right, let's do it, because we did spend a lot of time with Lucid Charts last week. And, honestly, given the conversation we had with folks and the interactivity, I think that was okay. I think we needed the time to build it up. So if you were watching this again for the first time and you're like, what are you talking about? Go back in our YouTube channel, which is very well where you may be watching this. I'll drop that in a moment as well. And there's a playlist there for this particular show. I'll drop the playlist. It's just the previous week. If you watch the previous week from last week, you'll get all the information that we had used to build up what we're just about to do.
Absolutely. And so part of what we're doing here is I have the honor to kind of walk David firsthand through the.
Let's not go too far. I don't know if it's honorable. No.
No, it's been I don't know. This has been a very fun experience, and we're basically live streaming David experiencing the content in the Practitioner's Guide to Graph Data, right in front of all of you all, which is incredibly brave and really fun. So I've been loving every moment. We've kind of set up chapter 8, and we set up why paths are awesome and why they matter. And so this is, you're kind of looking at the content that goes along with chapter 8 in the Practitioner's Guide to Graph Data. So if you guys need anything to be, make the text larger, just let us know in the comments. But yeah, so we're gonna start from the beginning here on chapter 8. Now we already have the schema and data loaded, so I think we're gonna go down to step number 3 in the notebook on the anchors there on the second cell.
We'll do going down to step number 3. Yeah, we already talked about the stuff. We've already preloaded it because we're in.
Actually, before you do all that,
Yeah.
David, can you go back up to the image that is the schema image from the book?
We'll just talk about that real fast.
Yeah, if you could just
Okay.
kind of bring folks up to speed in your own words, like what the example is about and what we're going to be doing.
Oh, right. So this is the one. This is where we started using weighted paths, right? So this is a little bit different because I'm going to try to paraphrase as best I can from what we've done previously. So in previous path examples, right, the path usually had a lot to do about distance, right? How long that path was from one vertex to another vertex. But in this case, now we brought in this concept of weighted paths, right? Especially if you're talking about, do I trust the person down the chain, right? How can I determine whether or not I trust them? Because trust is based on more than just distance between 2 points. So the weights in this particular case, and you can see here with our rated edge that we now have this new property, this trust property. And if I remember, the scale is +10 for the most trust and -10 for the least trust.
Absolutely.
And that we need to essentially take account of what the trust values are along particular paths to see whether or not in like a Bitcoin kind of thing, or, honestly, it doesn't even have to be Bitcoin. It could be any kind of trust network, right? Whether or not you actually trust the person who's at the end of a particular chain. Did I get that right?
That's perfect. And that's exactly what we talked about last week. And we haven't done the queries for either of them. So the queries we're getting ready to go through are going to start back at the beginning. And we are going to, so the wallet that we're going to be studying is wallet 1094. We kind of saw a preview of that last week.
Right.
Yeah. And so we're going to start by exploring some neighborhoods around 1094.
Okay.
And the next main section is we're going to do shortest paths just by number of vertices in between. So we're going to do shortest paths between 1094 and 1337, which there's a whole sidebar on why that is so funny to me, but I will just digress and move forward. And then at the end, we're going to look at shortest paths again, but then we're going to add in the total weight along the path. So that we
I gotta say, Denise, last week, so you kept chuckling about 1337, right? You kept chuckling about it, and the whole time in my mind, I'm like, is she making a leet speak joke?
I totally am.
And usually I'm the type of person who, if I'm wrong, whatever, I don't care. But I just didn't come out and ask that last week. And then so giving you like the fourth wall here. So behind the scenes, after we finished the show, one of the first things that came out of my mouth to Denise is, was that a leet speak joke? And she's like, yeah. I'm like, oh, because I would have joked about it or something. But yes, it's so if you were thinking, haha, 1337, totally leet speak, haha. Yeah, you were right. That's what it was. So
yeah, I don't know. Every now and then I guess I was like deep into writing this book, and it was probably some Saturday morning at some obscure hour. And I actually wonder if we might have this query here in the notebook. Let's scroll down. I was randomly selecting a vertex from the second neighborhood of 1094. And again, I don't know if anyone's going to ever believe me, but the first option was 1337. Anyways, it's okay. Don't worry about it. It's not going to end up being there. But it's cool. So actually one of these first queries is pretty cool.
Okay.
And what I'm doing here, so we're going to do a little bit of setup before we dive into shortest paths. But right here, this first query, I think we're just looking at how many addresses are in this data set.
Yes. You want to go ahead and run it?
Yeah, let's go ahead and run it. It's a pretty small data set. These data sets come from what is really popularly known as the SNAP, or Stanford Network Analytics Project.
Okay.
So this is the SNAP Bitcoin OTC data set that we've loaded into DataStax Graph. And it looks like, 5,881?
Yes.
Yeah. So that's how many vertices we have. And let's see how many edges we have. Can't quite remember off the top of my head, but this next one's doing an edge count, going across all of the edge tables and counting how many entries that we have here.
Okay, so we have 35,592.
Yeah, not too many. Small, small, tiny little graph here.
Okay.
Okay, so here was, I think this next query is what's going to take a significant amount of time to render.
Let's do it. So as I just hit the button, significant amount of time, go.
Yeah. Well, okay. So what I wanted to do is I don't know about you, David, but one of my favorite parts about working with Studio is using the graph visualization tool.
Mm-hmm.
And so what I wanted to do was just to look out across the person we're studying or the wallet we're studying, which is 1094. And I wanted to look at the different communities, unsupervised communities, kind of going into a little bit of machine learning.
Okay.
I don't want to say what community any one of these wallets or Bitcoin users belong to. I just wanted to see which ones that they belonged to according to who they've rated. And so what we're doing is we're starting at 1094 and we're going out and we're grabbing every vertex that is in its second neighborhood and we're displaying it. And on the settings, we can color the vertices according to a community detection algorithm. It's called Louvain, the Louvain community detection algorithm. And so that's what we're watching render here in Studio. And so I think this is just coloring potentially by, no, I think that already is set. Yep, it's set to color by the Louvain community detection algorithm.
Yes, it is.
Yeah, you can see different settings there. So for some of you maybe who haven't found the settings section, one of my favorite things is to change the icons just because it's really fun.
Yes.
Because we have a Bitcoin icon actually.
Oh, do you really?
Yeah, so you can click on address there and you can select Bitcoin, like the actual symbol.
Oh, yay. I didn't realize it was in there. Okay, boom.
And so I don't know, fun things that I spend way too much time doing in Studio. So it usually will. Yep, there you go. So re-rendered every wallet in our graph to being
just a couple. It's just a couple wallets. It's just
Yeah, so something fun to do in Studio. Do you do much, David, with the graph viewer?
Oh, I had at one time. Honestly, I haven't been working with it lately. So I haven't played there. So is there something new? Do you want to show me something? Is that what you're going to tell me?
No. I mean, I was genuinely curious. It's one of my favorite parts of using Studio. So I was really just curious. It's where I hang out a lot. I hang out here on this graph visualization. Anyways.
There you go. Okay. If you want to know how the mind of Denise works, she's hanging out here making pretty graph charts with Bitcoin icons. I mean, honestly, I can't blame you, really. It's kind of cool.
Well, and you can't be surprised. Like this entire series in the background, you've got 2 graph visualizations on my wall in my office.
I never noticed that until you just pointed it out, and I'm now looking over your head and I see them, and that is hilarious.
Wait, what? You didn't notice that this whole time?
No, well, honestly, I'm never looking over your head, right? And I'm honestly usually never looking over at your screen anyway.
Nice. Okay, well, good point. All right, well, sidebar for another conversation. Some other time. The images on my wall are the state of the United States, the state, not the state, but like they're displaying all of the healthcare transactions in the United States in the year 2016. Side tangent on what's going on up there, but that's another episode, another day.
Yeah, nice.
All right, cool. So just for those of you who were curious about how to use community detection with DataStax Graph, you can grab a large set of vertices and you can use the Louvain unsupervised community clustering algorithms to color your vertices and kind of see natural groups that are formed. But that has nothing to do with shortest path. So we are going to come back from that side tangent and move on.
And I do have one quick question, though, along the lines of community detection. So that's wonderful that you can visualize this, right? You can see it. Yep. Now, from a practicality standpoint, underneath the hood, now, is that just more for exploration, or is that something you see folks using in their applications? And if it is that exposed through the APIs? Is this something I can do with the driver?
That's a really, really great question. And the second part is yes, you can do community detection and get the labels. You're going to be calling that library directly.
Okay.
Probably using Spark graph frames for that.
Right. Okay.
Yeah. So that you can actually get the labels of your whole graph or some subgraph that you've selected. Cool. So absolutely, you can do that.
That's neat.
To your first question about why do people use it, actually, see, now you're going to make me talk about this image. The United States, no, it's okay. The United States image that's on my wall. maybe next week we'll bring up the zoomed in version of it. But the long and short of it is that we did look at communities, unsupervised communities of people within the healthcare industry in the United States. And there are different colors on this high-res image that I have blown up on my wall. And some very interesting behaviors did pop out that led us to finding a fraudulent doctor in the United States who was illegally billing our government for $20 million. So,
whoa!
Yeah, it was.
That's cool.
It was pretty cool. So yes, they do help, and they're very, very useful in different fraud use cases. But it's really easy to distract me with graph topics, and we've definitely done
no,
that.
we do need to continue on what we're doing here. So that's all right. That's a good thing, Denise. That's a good thing. All right, so I assume I'm going to move down.
Yes, yeah.
Just get away from that one. Get away from that one. Move on. All right.
Yeah, that is called distracted rabbit hole of not moving forward. Okay. So here's what we're going to do. We are going to start at our wallet that we're going to study, which is 1094. And we are going to look at the first neighborhood and just look at who has rated, or who 1094 has rated as a trust, like they trust them. Well, they gave them some value. We don't know if it's trust or not, but go ahead and let's just run that query. It's a first neighborhood query that we've done many times.
Okay, so we're just looking at the first neighborhood here. We're not filtering on trust or anything at this point.
No, we are not.
Okay.
But if you wanted to look at trust, we could, if that's something you're wanting to do.
No, I was just, given when you said what you said a moment ago, and I was looking at the traversal, I wasn't putting them together, so I wasn't sure I was in the right place.
Oh, okay, gotcha. Sorry, my bad.
Yeah,
My bad.
no worries.
Yeah, you're in the right place.
Okay.
So what you're looking at is just the total. You're looking at all of the other wallets in the data set.
I see.
1094 has explicitly rated.
I see. Got it. Okay.
I've given a trust rating to wallet 64 or wallet 1268.
Got it. Now we're not looking at those trust ratings here.
Not yet.
We're just looking at the fact that these are wallets that I have trusted or given a rating to.
Exactly.
Got it.
Exactly.
Okay.
Right. And so one thing you will note here, you don't need to scroll through the full list because I think there's quite a few. You will not find 1337 in that list. So there's 31 of them. So our target is to find a path between 1094 and 1337. So there's not a direct rating there between 1094 and 1337. So we need to find the path.
So there's not a direct rating in the first neighborhood. So, that's what you mean by direct, meaning this wallet knows this wallet directly and has rated it. So just by that, by that itself, we know that it will have to, as you just said, I'm kind of repeating what you just said.
No, that's great.
For my own mind, so I know. So then just because there is not that relationship, that direct relationship in the first neighborhood, we know that there have to be other players involved in order for that path to be established.
Exactly.
Okay.
And this is the exact same. We spent a lot of time talking last week about how this is a synonymous or a very similar problem to whenever you are looking at a LinkedIn invitation.
Right.
Right. So a LinkedIn invitation, you're not going to have a previous relationship with that person because they're asking you to be a direct connection on LinkedIn. And that's what we're doing here between 1094 and 1337. We're saying, hey, you guys aren't directly connected. So if 1094 makes like a request out to 1337, what do we know about the shared friends in common or shared connections in common to say whether or not we think they're going to trust each other? So that's what we're going to do with our shortest path application.
Okay.
Yep. Because that's what you do in your mind, right? So a new request comes into LinkedIn, and what's the first thing you do?
Well, you check out who they know. They check out if there are people you know. Right.
Yep.
And you check who your connections are. You check to see, how much can you know about this person or how much, you want to bring them into your network.
Exactly. And so that badge on LinkedIn, it'll say like second connection or third plus. And that's literally solving the shortest path between you and anyone else on LinkedIn and telling you how closely connected you are. So with a new data set, we're doing that exact same thing.
Got it.
Cool. So the second query that we have in the notebook, we are following the same patterns, just looking at now who's in the second neighborhood from exactly. We just walked out twice. We went from 1094 out to all the first neighborhood, out to the second neighborhood, and now we're looking at all of the unique entries there in the second neighborhood.
Right.
So It's the common boilerplate you've seen us do when we started with neighborhoods, and then when we started with trees. It's all about just making sure you can get the basics done in your data. So.
And something I think is always so neat is in the first neighborhood, right? We had 31 responses. Here we have 613, right? That feels like exponential growth to me, right? Just that, even just one step away from that initial first neighborhood, and immediately starts to explode a little bit.
Yeah, and I mean, absolutely, David, working with graphs is because relationships are the most important thing of what you're trying to solve.
Yeah.
And when you have so many different relationships between, people, et cetera, you are going to see that exponential growth. We talked about that. We call it branching factor. It was a part of the tree examples that we were doing. So
yes. Okay.
Cool. Trying to see what we are doing here with this query, because I think I'm ready. Let's just move on, because this one, we're just exploring more neighborhoods. I think we've got that. Let's move on away from exploring neighborhoods. Oh, and here it is. Here. Okay, so the answer's not saved, but this is the middle of a Saturday morning when I was writing the book query, where I was like, I need to find a random example, but I ran that, and I promise you it was 1337 the very first time.
Well, it does say random in it, and I wouldn't expect it to be the same every time.
Yeah.
Hence that part of it, but I believe you. I totally believe you. Totally.
There's the folklore that Denise did that. 1337 to get started.
And then it was 1337, and it just, you'd never expect that number.
Well, I really didn't, but Okay, cool. So I think we're ready for paths. I think that's what's next.
All right, let's do it. Shortest path queries in Gremlin.
Oh yeah, it is what's next. I really didn't know where the notebook was going, so I'm glad it's here. That's what we're doing. We're starting at 1094, and we are going to walk until we get to 1337. And so what we're doing here is, I think we are seeing the number of different ways that we're going to be able to form that walk. Because in some of the other setup queries, we realized that 1337 is in the second neighborhood.
That's right.
So technically, we already know how long the shortest path is going to be. It's going to be 2, because we're going to go from 1094 into the second neighborhood. We're going to find 1337. So this query is just discovering the total number of ways that we're going to be able to do that. So let's go ahead and count.
Yeah, because we found out last week when we talked about it, right? That yes, there's the shortest path, but there's all these other little paths that may be there depending on how many neighborhoods are between the first person, the last person, and how many connections they individually have. This could be, wild. It could vary wildly just off of, again, another neighborhood out.
Exactly. Yeah. Well, one more neighborhood out, we would definitely have exponential growth, and how many you would have here. But what this is showing is starting from on line 1, just starting at 1094. Yeah. Line 2 goes to this first neighborhood. Line 3 walks out to the second neighborhood. And we know from our setup that we did last week and a little bit today, we know that we're going to find 1337 in the second neighborhood. Right. So line 4 is a filter, and it's saying only the traversers that started at 1094 and finished on 1337 are going to pass, because has the true false filter. Right. And then we're just counting how many traversers that was. So 4. So there are going to be 4 different paths of length 2 to get us from 1094 to 1337.
Got it.
So we know the answer. It's kind of like we already know the secret sauce we're building up to. But really what we need is a query in Gremlin that's going to find the shortest paths no matter what. Right.
And without doing essentially with this hard-coded neighborhood thing, right? Where we're kind of going, well, I'll put both rated, I'm kind of gaming it, so I know exactly how many neighborhoods I'm going to go. But that may not be the full story, right? So you need something that's a little bit more dynamic, I guess, or organic.
Yeah, exactly. You want this to work for, an unlimited number of connections, or actually an unknown number of connections. Yes. That's why we're using graph query languages.
Are we talking about known unknowns, Denise? No.
We are talking about known unknowns.
I was actually making a funny joke from back in not only my defense days, but from the Donald Rumsfeld stuff from, God, was that 15 years ago now? But anyway, that's actually something, funny enough, that's actually something that we did talk about. We're known unknowns, unknown unknowns, all that stuff. But anyways, I was being funny, and then it happened to actually be what the case was.
Okay, David, you're the one who brings the comedic relief to the show. Like, you're always doing great at that. Like, you kill it. You're way better at me than these things.
The only, I just laugh at my own jokes whether or not they're funny. That's the thing.
That's okay. I laugh with you.
I'm happy that you do, because it'd be really awkward if you didn't.
Okay. So let's go write some shortest path queries, which so that our unknown can become known.
Oh boy. Okay.
So to kind of building up to that, building up to writing shortest paths, one of the pieces I always like to start with, that you guys have seen all the time when we're doing these queries, is that I start with very fixed known levels I'm walking out in my data, which we still have here.
Right.
And I spend a ton of time formatting the payload of my result, a ton of time. And I spend a lot of time there because it's really important that whenever you're writing graph queries, that you're adhering to some type of structured JSON that you're going to pass from this endpoint to some other part of your application. And so working with Gremlin to make sure that you can format those payloads is very important. And that's what we're doing here.
Right. Okay.
So what we're doing is we are just starting to format those 4 paths that we found in the last query.
I see. So this is the same up to this point. This is essentially the same traversal we were working with.
Right. But this time we're actually going to see those 4 paths. So we're still hard coding the number of neighborhoods we're going out. We're going to get rid of that soon. So that's going to be an arbitrary length, but just stick with us for a second.
Got it.
On line 5, every one of the traversers that does arrive at 1337, we're saying, hey, give me your path. And so we stopped at vertices along the way. So that path is going to be a list of vertices. So on line 6, we're saying how we want that path to be formatted. And we want to format it according to the key of every vertex. So that by modulator says, awesome, for every vertex in my path object, display its public key. And we're just going to be storing that as the traverser path values. We don't need to worry about that as statement now.
Okay.
And then the last thing that we're going to do on line 7, we want to say, well, how long is each of these paths? That's what the count local does. Count local is saying for each of the 4 paths, tell me how many vertices are in each path.
Okay. Right.
Okay. And we're going to store that as a variable called total vertices. And then at the end, what I want to do is I want to format my path to show me the vertices along the way that we saw, and then the path length. And that's what I'm doing on line 8. So I expect a table, and I expect that table to have all of the vertices, and then that I went on the way, and then the actual number of vertices at the end. So there you go. So we expected to see 4 paths. We see 4. That middle column, the longer column, is showing you the vertices that we stopped at along each of the options. And then it's counting the total number of vertices in each of the objects on the very final column.
Okay. Yeah.
Thoughts on that? What surprised you? What did you not expect to happen there?
No, it wasn't anything that I didn't expect. I mean, I guess the labels on objects, the way it displays, funny enough, you may have seen me kind of click in for a moment. I was actually looking for the JSON object little widget that usually is in Studio, but then looking at...
It's right to the left of the table up on top.
Oh, true. There's this one, but I'm talking about when you display JSON, but this actually may not... As I'm looking at that, I'm like, actually, is that JSON? Because usually when you're in the table view, the grid view, and you have JSON and object, you can click on it and it'll expand it out in the details, the cell details. And so for a moment, I was looking at it. But no, the data itself makes total sense, right? I mean, as you explained it, this is showing me the path from 1094 to 1337. And, and obviously, again, our contrived case where we're only going out 2 neighborhoods and then the total vertices. What I like about this, and to your point about, like,
I don't know, David, if you can still hear me, but I seem to have lost your audio. Hold on there, guys. If we are still live, I have lost David's audio. And Gonna go see what's going on. One second, gonna go troubleshoot some of the background items here because I have lost connection to David. Right when we were just in the middle of getting to the shortest path options, which was the the meat of what we are here to do today. Let me check one thing real quick, folks. 1 second. I'm gonna put myself on mute for a second, guys, and go see what is happening. 1 second, I'll be right back. Okay, so it looks like David has lost connection. David has lost internet. I don't know of any. I hope he's not in any areas where there is some type of natural disaster. Actually, I'm pretty sure he's not. For where we were walking through the shortest path queries, and I was teaching David to see where to kind of get to the final sections of the shortest path query that we were working on. I do not have that content pulled up here. Yeah. I just saw Frank's comment on YouTube. Yeah, for David has lost his connection here for the day, and we were in the middle of walking through our traversals and our queries. So as we wait for David to get connection back up, looks like he's going to be able to join back here shortly. Thank you all for your patience as we try and troubleshoot what is going on. But it looks like it shouldn't. Looks like something he should be able to figure out. So no worries. But for where we're going to go, as we get David back into the broadcast, we are going to kind of finish. We're gonna next look at how you're going to write a Gremlin query that is going to find the guaranteed shortest path for any pair of starting and ending vertices. And we're going to show it for the example that we're working in, but this also can be used for any graph database that uses the Gremlin query language to make sure for two inputs that you have the exact shortest path between them. And it looks like David is back. Everything okay?
What's funny is I heard the thunder out in the background, and then also my network just went boom. And we do get pretty solid storms where I live, so I wonder if something got knocked out somewhere. But anyway, I am back now.
I'm glad to see that you were safe for a second. I was sitting here trying to remember, oh gosh, do you live somewhere in the United States where there's a natural disaster happening?
Every day at around in the afternoon, we have, according to some places I live, like if we got the amount of rain in LA when I used to live in LA that we do here in Central Florida, LA would have been washed away a long time ago.
Got it.
All righty. So I'm assuming that you were. It sounds like you kind of kept going there, and that you were talking to the traversal we had up, or do I need to move on?
No, we were just kind of talking about where we were going, and Frank had mentioned that my video is frozen, so hopefully it is back. It looks like it's working from my view. Thanks, guys, for your patience as we work through that. But yeah, I think where we are is what we just did before you dropped off, David, is that we had created two custom views into our path.
Okay.
The first custom view is called total vertices. Well, actually, the first custom view is called traverser path, and the second view was called total vertices. So this traverser path object that we're saving is the list of vertices that are on the path. And then the total vertices just counts up. It counts up the total number of vertices on each.
Right.
So
yeah, and then just to kind of summarize what I was saying as well, from a point that you made, is essentially using this traversal with kind of some of these hard-coded values, right? That we kind of know what the expected output is. So then I know for me, I've done development with traversals. This is exactly what I would do. I would start with the known quantities in my Gremlin traversal. Then I would work out what I wanted the output to look like in my code.
Exactly.
Then I would go and started adding the complexity and such to the traversal because I know the output is what I expect. So you asked me a question earlier, did I see anything wrong or was this not what I expected? And after I kind of understood what I was seeing, I was like, no, this is exactly what I would expect to see for this case. So I know I can start building the complexity from here.
Absolutely. Perfect. So what we're going to do, because that's absolutely right. And I love hearing that. And hopefully after, I love hearing that because that is how I work and develop new Gremlin queries. And I'm hoping that those who've been following along with our series are starting to pick that up as well for how you kind of create new Gremlin or new graph traversals. So what we're going to do is we're going to skip through, I think the next query, just so we can get down to the real, this next one we're going to skip just because I was, next one we're skipping. It's finding paths of length 3, which, by the way, for the keen observer, curious, David, I had mentioned that our path is length 2, but our payload said 3. Do you happen to know the difference? I don't want to put you on the spot, but I'm curious.
No, let me look at it here because we're counting. I mean, if we're counting, aren't we counting the total vertices though? So even though the path length, the number of neighborhoods is only 2, we actually have 3 vertices in each case.
Exactly. So path length refers to the number of edges.
True.
Perfect. When you talk about path length, it's referring to how many edges you are away. And then the vertices, when you count total vertices, you have a beginning and an end. So you're going to end up with 1 more. So. Okay. Perfect. Okay. So we're going to scroll on down to the secret sauce that everyone really wants to learn when it comes to Gremlin, which is let's scroll back up one query, I believe.
Finding paths of any length.
Yep, finding paths of any length. Now, do not run that.
Okay.
Please don't run it.
Yes, I see the note and I see what it's doing, and yes, I understand.
Okay. So the only difference in the query that we just saw and this query is that we took that boilerplate of walking out a fixed number of out steps, or the boilerplate of saying repeat X number of times. And we're wrapping it in the repeat until pattern. And so lines, I think 1, 2, and 3 are doing shortest paths, start at 1094. Line 2 says, keep walking out rated edges. And then line 3 says, until you get to 1337.
Okay.
That is the power of why people love graph technology, because you can't do that in other, like in SQL. Like you cannot write 3 lines that are going to crawl every single potential edge or join table you can think of.
Right. That's some hairy SQL.
Yeah. To just discover the path in your data. But the reason I'm saying don't run this one is because this is finding every and all paths between 1094 and 1337. And we saw that, how many thousands of edges did we have? Like 35,000?
Yes, 35,000 edges.
Yeah.
Right. Yeah.
Right.
It's gonna. I see now.
and for, I mean, it's going to be every combination of those 35,000 edges that you can find to walk from 1094 to 1337. Every combination. Huh. So we're probably talking about hundreds of thousands of ways to walk.
Yeah.
Between 1094 and 1337. So that's what that is going to compute. So instead of doing that, we just want the single shortest path.
Okay.
The single shortest one. And I'm going to go into the weeds for 2 minutes. We're going to quickly go in the weeds and we're going to come right back up. So I'm going to give you the answer. The answer is to add limit 1 to the query above. And here's how you know that works. So we talked last time a lot about doing depth first search versus breadth first search.
Right.
Remember that? So if you're wanting to kind of think, well, how do I apply that to Gremlin traversals? It is a very long topic, and we go into it in depth in our book in chapter 8. But the long and short of it is that you want to see if there's a barrier step in your query. And that's what we do here in the next one below. So if you go down to that next box, you see the explain step that we have?
Yes.
The explain step allows you to understand if there are any kind of barriers or other types of path optimization that's happening in your Gremlin query. And so I do believe that should work now. We just recently added the ability to see those results. So let's go ahead and run that. And perfect. So what you're seeing here is you are now looking at all of the different ways that traversal is optimized from Gremlin into Cassandra. And it's going through all of these different optimizers. And when I look at this, I look for a barrier step or a barrier, and it's in there somewhere. And so what that's doing is when you see barrier, you loosely in your mind can think breadth first search. Now, it's not a perfect analogy. And I'm sure that those who wrote Gremlin are gonna be like, oh, that's a little rough. And that's true. That's true. But that's the way that I like to think about it. Trying to bridge those concepts together. If there's a barrier in my Gremlin query, it's going to be roughly operating like breadth first search. It's a loose analogy. Just go with it.
Okay.
So let's scroll down, and what we're going to do is we are going to make sure that we add one step to our query to get the single shortest path, and this is it. So the query above that I said don't run because it was all paths. All we added on line 4 was limit 1. So that means I want you to start at 1094. I want you to walk out into 1337, which is going to do essentially a breadth first search style of walk through your graph. And line 4 is saying, I want the very first one that finds 1337, the very first one. And that's going to be guaranteed to be the shortest one. So we can go ahead and run that. And it's going to return the single shortest like path of length 2 that gets you from 1094 to 1337.
Okay. Now here's a question for you.
Okay.
Why not just do simple path?
So simple path is something different. Simple path removes cycles from.
Right.
From
so that's not really going to get me the same thing. I see. Okay.
Yeah. And so when we're doing this, I mean, we knew we had 4 short paths of length 2. And so this is just giving you the first one that it finds. So if you wanted to pick like any other vertex in the graph that we should figure it out on the other side, like you can just change these starting and ending points with limit 1, and you're going to get the single shortest path between your 2 vertices in your graph.
And is that always true? So no matter how many times because we know that there are multiple paths, right? There are multiple paths from 1094 to 1337. And there are multiple paths that have a total vertices of 3. There's 4 of them.
Yep.
So now when I run this every single time, any one of those could be a candidate, right?
It's the first one that is found. It's the first one that is found, and any one of those can be a candidate. So it just depends on which one does get there first. But
and for our criteria, that's okay.
And for our criteria, that is okay. Yep.
Okay. I see.
And I don't know, for those of you who are thinking about graph applications, this is huge. Like this query and how you can so simply start at one vertex on line 1 and say, I want you to keep walking through edges until you get to this vertex on line 3. And then line 4 says limit 1. Those 3 lines of boilerplate code in Gremlin, for whatever start and whatever end you put in there, is going to give you the single shortest path by number of vertices along the way. That's the gold that you can take and go to your other shortest path applications.
That's cool.
Cool.
And you can't see my face. That one's got me grokking a little bit, right? Like,
okay, what are you thinking?
It's just the amount of, how do I put it? I don't want to say like the amount of power in the graph database. No, it's like just the way, and I'm also kind of mentally imagining what this may have taken me to do in SQL and to do in a relational way. And this is just one of those areas where at first, when you're starting to work with a Gremlin language and you're starting to work with graph databases, and so many of us have come from doing things with relational databases in SQL for a long, long time. Mm-hmm. And so at first it's like, okay, I've got to learn this other language. Why is it shaped this way? Why are some of the function calls look like this? Why is it weird and everything? But then as you start to run into examples like this, where you can see what you can actually do with it once you start to get some patterns under your belt and everything, and the amount of work that is actually being done in those 3 lines compared to what I would have done before to do this in SQL is really kind of mind-boggling. And it actually goes back to something we talked about many sessions ago in this series, which was the SQL to Gremlin site, right? It was one of the first things I came across when I first started doing Gremlin. And again, the point isn't to be like, oh, SQL bad, Gremlin good. That's not it. It's not it. These things, it's not about the language or whatever, but it's, I was just having this conversation with somebody actually the other day that Gremlin was purpose built to work on these kinds of problems.
Exactly.
With graph databases. And when you start to kind of see what you can do with it, and some of it makes sense. I just had a moment where I was like, that's pretty darn powerful. That's just like really cool that you can do that kind of thing of it so easily once you understand how.
Exactly. Like the, I will say, I've said this publicly before. I mean, it's not that Gremlin's easy to learn,
right?
But to your point, once you really understand how it is working with your graph data, in 4 lines, doing shortest paths across 2 points on a graph in 4 lines. Yeah. I mean, I don't know. That's why I really love it. And
it's almost too simple in a way. And well, again, I totally agree with what you just said. Gremlin isn't always the easiest language to just pick up and learn. But as you start to understand its patterns and everything, it becomes really, like I said, it becomes really powerful. And the simplicity of what's going on in the traversal here almost undercuts the complexity of what's really happening.
Yeah.
And what it's doing for you. Right. Yeah.
Yeah. I mean, it's insane to realize how this language works and how it was designed and the power that it has. It's one of my favorite things to think about. But I do want to kind of go back to one of your questions to make sure it's really clear, because you did bring up a good point, which was that we know there's 4 short paths, right?
Mm-hmm.
So this query with limit 1 is going to always give you one of those paths.
Yeah.
One of those paths. So it's a shortest path, not the, because
correct.
Because in this case, there's 4. So it's going to always be one of the shortest paths.
And that's exactly what I meant. But when I said per our criteria, that's okay. We weren't asking specifically or explicitly for the only one path. No, it's like, give us the shortest path where there are 4 answers.
Yeah, exactly. So I wanted to point that out. Thank you, Daniel, so much. Daniel was still continues to be an incredible colleague and resource. He was one of the editors of my book and this work. And I always cherish every hour that we got to spend together working on these queries. So I really appreciate you with that distinction, because I want to make sure that some of those details we do accurately represent. So thank you very much for that. Right. So here's what I want to do. So we have a query. Line 4 is give me the first path that gets found. And it's because it's 1, it's going to be one of the shortest paths.
Yep.
We can play with that limit variable, and we can say give me 10, give me 15, give me 20. And we're going to start getting lots of paths, but we can order them different ways. We can order them according to the total number of vertices. We could order them according to their path weight. So let's go a little deeper.
Are you playing straight person here, Denise?
Maybe. Yeah. So let's. What I want to do so that we can wrap up the examples today is I want to get to ordering these paths by their weight.
Okay.
Because that's going to be a big chunk. So on this next query, let's see where we're going. Right. So the next query, all it changes is how many paths we find. So this time we find 15 shortest paths. So, and we're going to look at them according to the vertices visited and then the total number of vertices. So go ahead and run that. And in Studio, when you have these results, when they're formatted in a table, when you're in Studio, you can sort them according to the different data that we have in the table, and they're going to come out in order because you find the shortest ones first, and then you find longer ones.
True.
But it would be great if we actually had that sorted order guaranteed. So that's what we're going to do in the next step. We are going to take all of these paths and then start sorting them according to the total number of vertices that they have. But I actually think I'm lying to you. I think I see that we're summing on, you see line number 5?
Yes.
Line number 6, is that by rated?
By trust.
Oh, perfect, by trust. So we are in this one, we talked about doing weighted paths. So I apologize for the verbal setup there. I thought it was going in a different direction. So let me rewind for 20 seconds. In this query, what we want to do is we want to find, say, the 15. Is that 15 on line 9?
Yes.
Okay, cool. So we're going to find the 15 shortest paths according to how many vertices are in that path. So you're going to have one path of length 3, or one path with 3 vertices, a bunch of paths with 4 vertices, and then you start to see a path or 2 with 5. But this example has to do with trust, and trust is an edge weight. So we want to actually start adding up how much trust we observe on these paths.
Right.
Yep. And so we want to actually look at like the total trust of a path. And that's what we're going to start doing. So on line number 3, we actually on line 1, we did this in the last chapter where you say, all right, I'm going to give every traverser a backpack, and it's going to have 0 in that backpack. And what we want to do is we want to add up these trust values as you go. And so we're going to do the exact same query, start on line 3 at 1094. And on line 4 to line 8, you see that same boilerplate of repeating doing some work until you reach a destination. So we're going to repeat doing some work until we get to 1337. So let's talk about what that work is. So from 1094, we're going to ask every gremlin or every traverser to walk out to an edge called rated. And we're asking it to stop on the edge. And why are we doing that? We need to stop on the edge because that's where the weight is stored for your trust.
That's right.
Yep. And so we say, hey, we have a backpack on. So we're going to ask you on line 5 to add something into your sack. And what we want to add into the stack is the trust value that you see on that edge. So add into my stack the value of trust that I'm currently on that edge, add it in there, and then I'm going to keep walking. I'm going to walk out to the next vertex, and that's what happens on line 7. And we keep doing that until you reach to 1337. And we're going to allow the first 15 traversers to reach 1337 to pass. Like the first 15 are the ones who get to move on. Everyone else after that, if you didn't make it in the first 15, you're out.
That's right. Okay.
You don't get to keep going.
You got to have some kind of limits here.
Yeah. Otherwise, we're going to be finding hundreds of thousands, potentially an infinite number of paths.
Right.
So on line number 10, that's when we start doing some formatting of your results. So hopefully over the series, you all have figured out that Denise loves project by patterns. So I want to
project by, just to mention from a developer standpoint, is actually really useful. I used to use that pretty exclusively when I was massaging results in my code.
Exactly.
Right? Project by was extremely useful for that. So this is what I would use in code.
Exactly. So we make 3 keys in a map: path information, the total number of vertices and edges, and then the total number of trust. So the by modulators on line 11 give you the values for the first key, path information. The by modulators on line 12 give you the values for the second key, and so on. And so when we're doing this, the first one for path information, what we want to do is we want to look at the paths, which are going to now be vertex, edge, right? So we're going to get the path, and then we want to see the ID of the vertex, and then the amount of trust on the edge. And so that's that massive object that you see where it says 1094, and then it has a value, and then it says 1268 and a value. So you're looking at the actual path and the ratings along the way. There you go. Perfect. Yep.
Got it.
And so that next column is adding up the total number of vertices. Now we're counting local. You're counting the total number of objects in your path. We've got vertices and edges this time, so we expected that to be a little bit more. And that last piece, you were just saying, hey, on line number, I think 13, you're saying, hey, how much have I stored in my sack? I was adding up all of those trust ratings along the way, and that's what you see there on the end.
Got it.
The total number of the total trust. So this is the setup for getting you into doing shortest paths by weight, because you eventually want to sort the weights and rank them highest to lowest weight. But we talked about this last time. Can we really say that like a higher weight here is going to help us find shortest weighted paths? And it's not.
No, right? Yeah. Matter of fact, I mean, there was a question that was burning in my head as I was looking at the data. I mean, right away that you can see, even if you had someone on a particular path that had multiple links that were rated very low, a -10, depending on what the rest of those looked at, you're just adding them and just added it. So if you had a longer path and you had enough rankings that were, weights that are relatively high enough, they essentially could negate all those negative ones. And just because you have a longer path, that doesn't mean you have more trust.
Exactly.
right? Like there's something, there's more here that we need to do to really get at our answer.
There is. There is a lot more that we need to do to get into the answer. And for where we are in this series, we're actually going to leave it here. So
Ooh.
I know, right? So we're going to kind of leave
Is this-
paths on a cliffhanger.
Is this the end of season cliffhanger?
This is. It's the end of season cliffhanger. Let me just let you know exactly where you are.
Yeah.
You have a 4-line boilerplate for how to do single, like shortest path between a start and an end using Gremlin. And that was where, you start at 1094, you walk out edges until you reach your end, limit 1. By far, that is like the most useful path query that any graph developer is going to want to use for shortest paths. If you want to get into doing shortest weighted path, there's a lot more to do. And we are going to leave that up to those who want to follow along in the Chapter 9 notebook and follow along in Chapter 9. If you all want an access code to reading Chapter 9 online for free, I will happily give it to you. Just send me a note on Twitter. I'm at Denise K. Gosnell. Send me a note on Twitter. I'll give you the link of how to access the full book on O'Reilly's learning platform. For 30 days. So you can dive in and you can read how we do shortest paths, shortest weighted paths. But for where we are in this series, we wanted to get you guys to understanding 3 basic things: how to use neighborhoods, how to use trees, and how to use paths. Because those are the 3 fundamental concepts of how people are working with graph traversals in production applications. And we're there. Like, we just got to that. So David, here's what I want to do next week, or what do you think for this? So next week's going to be our last show. What I want to do is I want to set you guys up to be able to use these fundamental pieces, but apply them to doing how Netflix does recommendations. So in the last 3 chapters in the book, which again, if you want access to it for free online, tweet me, I'll get you a code. When you're doing recommendations with Netflix, you're essentially applying collaborative filtering. But at the end of the day, if you can understand neighborhoods, if you can understand recursion through trees, and you can understand this idea of a path, that's all you need to be able to apply it to do collaborative filtering, which we walk through in chapters 10, 11, and 12. But I'm going to leave that up to you guys if you want to go through the notebooks and ask me questions online, because next week will be the last show. So we're going to get you set up for how to do that and how to get started with doing collaborative filtering, and show you a few of those examples. But then we're going to leave the rest to you.
All righty. All right. Well, with that, we are at time for today. It is 1 o'clock, at least my time. It's 1 o'clock Eastern. So thank you, everybody, yet again for coming and joining us today during our Graph, Data, and Code show with the wonderful Dr. Denise Gosnell, who somehow is able to explain things to me in such a way that when I repeat them back, at least they sound somewhat similar to what she said. So that's good. No, honestly, I've learned myself. I've learned a ton on the show. It's kind of a fun highlight of the week to be able to come here and talk with you and kind of go through all this stuff. So I hope everybody else watching has as well. And we will see you.
Maybe next week is your final. I don't know. Maybe next week you should be the one who walks through.
She's gonna put me on the spot. Yeah. Oh boy.
No.
Oh
Yeah.
boy.
No. But no, we in the movie data that we're going to load up, it's the movie lens data merged with Kaggle's movie data. So like I already did all that merging for you guys. So hopefully you find that valuable. But yeah, if you want to, we can kick you off and have you do the neighborhood queries and the paths and the trees, and I can help you out. But basically we apply these patterns to the most popular movie databases before we do collaborative filtering. So sounds like a great place to apply and make sure that we've got the basic concepts down next week.
Yeah, and I would also think that next week might be a really good time for those who've been following along and you want to take on Denise's challenge. That's a great time to come and then ask us questions about what you have gone through, right? And about that experience, because you're going to have Denise's ear. And then we get to put Denise on the spot. So
yeah, that sounds great. Yeah, let's just bring all Gremlin questions next week, and we'll apply them to the movie data and see what we find, and end the show with some fun live questions. And I guarantee you, if Daniel comes and starts asking questions, I'm going to have to ask him for the answer. Awesome, guys. Well, thank you so much for hanging out.
All right, thank you, everyone. See ya.
See you next week.